Good afternoon, everyone. Welcome to this afternoon's presentation on hydro brakes for flood and flow control. My name is Philip Taylor. I'm Hydro International's product specialist for the stormwater products. I've been with Hydro International for about 12 years now, working primarily in the flow and treatment products. I enjoyed putting this presentation together for you. I hope you enjoy it. Now, bear with me while I work through the glitches of getting technology working. Okay, so first I'm just going to go through a bit of housekeeping, talk a bit about Hydro International. I'm going to go through and show you how the hydro brake works, and then run some applications rather than sort of talk too much about the product. I want to demonstrate how it works and then give a few examples. I want to introduce the hydro brake flood valve, and then just briefly go over the sizing tool, which is available on the web now. At the end of this presentation, we do like to have a little exit survey that gives us some useful feedback. It's a 5-question survey. It should only take you a couple of minutes to do. We really appreciate it if you stick around and do that. And for those that do stick around and do that and complete the survey, someone will win a $50 Amazon gift card. And for those that need PDHs, our administration people tell me that tomorrow they'll send out PDHs to everyone that attended the webinar. We had over 200 people register for this webinar, so thank you very much for registering. Currently, we're well over 100 people online. It's good to have everyone on board here. I'm recording this presentation, so if you want to review it afterwards, it will be loaded up to the Hydro International website and also our YouTube channel. I've also attached for your information, you can download a copy of this presentation in PDF format, and also a couple of case studies that illustrate some of the design processes that I'll go through in this presentation. So there's some additional information there. For those of you who have been on this webinar before, you'll know that Hydro International, we've been around for many years now. The company was basically founded in the early 60s. We have many decades of experience and many thousands of installations of vortex valves, hydro brakes, and treatment units worldwide. One thing that Hydro does have is a really good hydraulics lab, and I'll go over that shortly. Our primary areas of business are stormwater, wastewater, and combined sewer overflow. Now, the products tend to overlap a little bit. The technologies are the same, but I'm just going to concentrate on the vortex valves in the stormwater application. Hydro as a company has a worldwide footprint. We do business in over 33 countries, and there's approximately 200 plus employees in the company now. Research and development is a strong part of our business. The company was founded on a strong research and development foundation. We collaborate with universities and other research institutes, and we spend a lot of time. In fact, one of the biggest costs of our business is obtaining our certifications and approvals to use and sell products. So we do a lot of that as part of our day-to-day routine, is getting certifications and approvals and making sure our products do what we say they do them well, and that the product is fit for purpose. Within our stormwater line, we do separators, we do stormwater screens, stormwater filters, and the hydro brake vortex flow control valves, and that's what I'm going to concentrate on here. So just to get started, it helps me, and I think it helps everyone else. We just have a little bit of a quick poll to get some idea of the audience and what their understanding is of the product that I'm talking about. So I'm just going to launch this first poll, and I would appreciate if you just take a few seconds to click on it. And then after about 15 or 20 seconds, I'll close the poll down. Okay, we're just about done. I'm going to close the poll now and take a look at the results. And as you can see, approximately 46% or almost half the people online, really it's a new product to you guys. So thank you very much for coming along and learning about a new product. Approximately 25% of the audience have some idea of the technology or have used it. And we appreciate that. And well, I can see a typo in the poll, but never mind. 31%, I'm not sure what it is or have no idea. So let's just move on here. If I can just close this. Okay, so vortex flow control valves. There's a family of valves here. We call them the optimum range and the hydrobrake flood alleviation range. Now, within the optimum range, we have two basic valve shapes, and that's the S type, the one on the left. That's a snail shell type, hence the S nomenclature on it. The C, which is a conical shape, and the flood control. The main difference between the S and the C is that the S-type valves have a submerged sump, where the C-type valves have a matched level invert, so they drain down the upstream structure completely, and the S-type will actually retain a wet sump. Every valve is a custom build. These aren't sitting on the shelf. They're not a off-the-shelf item. You just can't go and buy one. So there is a lead time on these. Everyone is built to a specific design. Everyone is built to a specific mounting detail. So it is customized for your job. All the valves are manufactured in the UK at present. They're all made out of stainless steel. And roughly the lead time from ordering to when a valve arrives is 2 to 3 weeks, so that's not too bad. The manufacturing facilities and jigs for these valves are complex, and the skill to build them is high. And so currently they're all manufactured at a central manufacturing place in the UK. Just a bit of history on this. The vortex flow control valve is not a new product. One of Hydro's founding fathers, Bernard Smithson, actually invented the flow control valve to solve a problem with controlling flow in combined sewers. Incidental to that, when he was spinning the water in the flow control valve and doing experimentation with cyclonic flow, he also found that spinning water inside a chamber altered how the grit settled, and from that, he did research and developed the first hydrodynamic separators. Now, since that time, Hydro has continued to develop the vortex flow control valve technology. Within our staff, we have two highly skilled engineers who do the modeling, development, and analysis of our stormwater flow control valves. And Hydro is really quite enviable in the position that we have probably the most skill and experience in these valve designs and product development than any company has in the world. Now, to support that, we also have a couple of world-class hydraulics labs. One is actually located here in Portland, Maine, and that one really does a lot of research into the swirl separators and treatment devices. And this one actually is in the UK, and it specializes in the study and research of vortex flow control devices. So how does a valve work? Well, hopefully this is going to work for you guys. This is a video showing a Perspex clear valve that you can see. And as the water comes in, a head builds up, and the whole working mechanism behind a valve, there's nothing inside it that moves other than the water. So it's a non-moving part item. And as the water comes in, the shape of the valve creates a spin. And just like water going down a plug hole, that spin creates an air core. And that air core chokes the water back as it exits the valve. So in the initial stages, these valves have a large opening and the water can pass through quite freely. But as the head builds up, they actually slow down. So you actually get a decreasing flow with an increasing head. And that's the crux behind the valve. That head discharge curve is unique to a vortex flow control valve. And it's that discharge curve which gives us many of the advantages of using these valves over standard orifice controls or throttle pipe controls. Now, in developing these valves, it's important that there be some sort of trail. You just can't make a product, put it on the shelf, or put it on the shop shelf and say, buy it, it works. Hydro has spent a lot of years dedicated themselves to developing these valves. So the original design and research valves still exist. They're on a shelf in a lab. So if anyone asks, where did this all come from? We can pull those valves out and reproduce the original design experiments and prove that these things work. And in more modern times, we use computational fluid dynamics, and we calibrate the computer models against the original designs. So basically, this is a long-term empirical research project that's taken decades to get to the point where we are today. Of course, we just can't say, okay, believe us, these things work. We send our valves out to a third-party certification body, and that is actually the British Board of Accrement and the Water Research Centre in the UK. Now, these two do certifications for structural and hydraulic checking. So they study the research and will certify that the valves are fit for purpose, that they do what you claim they do within a certain tolerance, and that the engineering and science behind them is valid. Now, this is probably the only certification that can be provided, as there's none in the US. The equivalent would be something like ETV or NJCAT within the stormwater treatment industry within the US, but there's no place that we can take these valves currently in the US, so we use the UK certifications. So where would you use these valves? Well, one of the main reasons you would use a vortex flow control valve is to improve the hydrograph modeling between an inflow hydrograph and an outflow hydrograph, which is often used to size storage systems. And this can allow you to shorten the detention time and actually reduce the storage system. Another way of using a valve is to improve the outlet condition and robustness of a design. This is getting pretty common now. I get many questions about how to get an orifice control up to a minimum size. Typically, we're seeing stricter and stricter release conditions where you've got to get back to pre-development or even pre-settlement release rates. And to do that on a small site often means a very small orifice control, usually less than 1 inch, or say 25 millimeters. And as this graph here shows, I can do the same discharge rate with a valve that is approximately over twice the size in a vortex valve. So that makes your design more robust, less likely to block. And these are advantages when it comes to designing a site. The other reason you use a vortex valve is that there are cost reductions associated with more efficient tank design. And we'll go into this a little bit later, but this is actually one of the case studies you can download, the Chevy Chase building in Maryland. It was configured around a local regulation that said you've got to have a minimum 2-inch orifice and you had to store a certain amount of water. By using a vortex valve, we could reconfigure the footprint, reduce the volume, and the valve, I think that one sold for around $3,000, but ended up bringing back about $150,000 in cost savings on the project. You can use a vortex valve with just about any storage system, whether it be above ground or below ground, proprietary system, tanks, StormTech, ADS, StormTech chambers. It really doesn't matter what the storage system is, the vortex valves can be used with them. Now, typically speaking, when switching from, say, an orifice control to a hydrobrake vortex valve, you'll see a saving in volume, depending on the storm type and the hydrograph used, in the range of 5 to 50%. Now, you're not going to get 50% every time, especially with type 2 storms that we see used a lot here, which have a very narrow and high peak. We really like to see hydrograph modeling with storms that have a more of a shoulder side, more lead in and more lead out. That's where the valves really leverage their advantage. But when we look at the flow discharge curve here between the blue line, which is an orifice control, and the red line, which is a hydrobrake, you see the shapes of the curves are different, and that the volume is represented by the area between the two curves. And that can be quite dramatic in some cases. So if we plonk those curves onto a idealized hydrograph here, the total area under the hydrograph is the volume of water that's dropped in the rainstorm. And the area below this blue line here is the discharge volume for the orifice control. The area above the blue line would be the tank volume that you're required to design and build to store the excess water. When you take the hydrograph and the discharge curve for a vortex valve and overlay the two, what the vortex valve allows you to do is get up to your maximum allowable discharge faster, stay closer to that for longer, and then over a shorter period drop off back to original base flow. But the pink area is water that you've discharged. You didn't have to store it because it was coming in at a rate less than your allowable discharge, so there's no reason to hold it back. You could let it go straight through. And that's a reduction in volume. So just want to do a second poll here, just a quick second poll to get some idea of what the main problem is that perhaps you encounter when you're working with detention systems. Okay, that's an interesting poll. I'll just share the results with you. Now, it's quite a strong result there for footprint. That footprint is a big problem. Now, that's interesting because footprint is a function of the outlet control, and I'll go into that. As soon as this presentation lets me move to the next slide. Okay, so let's look at the footprint question. Now, this isn't a predetermined result, it just happened to fall this way. If I look at, I live in Madison, Wisconsin, which is just north of Illinois, Chicago area. Chicago is an area where vortex valves are used routinely. And one of the main reasons is the City of Chicago discharge regulations on small sites. A site between 0.5 and 1 acre has a discharge limit of 0.15 CFS with a minimum 3-inch outlet. A site between 1 and 1.75 acres must be held back to 0.25 CFS with a minimum 4-inch outlet. So that gives you a couple of constraints of both the flow rate and the outlet size. So let's say we model a site and just assume an underground tank, a cubic sort of tank, 1.75 acres using Huff distribution. That's a broader distribution than the type 2 distribution that we see in most of the Midwest. The Huff distribution is one more applicable to the central Midwest area. If we look at, say, 6 inches of peak rainfall and a highly impervious site with a CN value of 98, typical of these intense inner city sites. If we do a model on that, we find that the peak rainfall, 6 inches, is producing about 0.87 CFS, roughly 26.6 litres per second inflow. We've got to limit that to 0.25 CFS on the outflow side. So I can do some modeling in HydroCAD. You can do modeling in various modeling software packages. I'm not going to go into that. You'll be familiar with the package you use on how you do this, and the vortex valves can be used with most of these packages. So I can just go in and estimate using HydroCAD the approximate volume that I need to size my pond for, and to pull back to about 0.25 CFS, I'm going to need roughly about 0.55 acre feet, or around about 680 cubic meters of storage. So just doing a few little calculations and make some assumptions. Let's assume we've got about 6 feet available head on that site to build our storage pond in. We have a 4-inch minimum orifice because of the site size. So roughly 0.55 acre feet, 23,958 cubic feet. Let's assume that we want to put a water level in there about 5 feet deep. So if we just divide by the depth, we get a footprint area, roughly 4,800 square feet. And if I just take a square root of that, I get a roughly 70 by 70 footprint. So I do my model and I throw a 4-inch orifice in there and just run the modeling software and see where that leaves me. And what I find is that 4-inch orifice using that size tank is going to discharge with about, I'm assuming about 100-foot invert, so it's 2 feet above invert at 102 feet. So I'm only using about 2 feet of that tank and I'm over discharging. I'm at 0.57 CFS. So that's not going to work. The regulator's not going to approve that. It's not an efficient use of the storage volume either. But here's my problem. Regulation says I've got to get 0.25 CFS and I've got to use a minimum 4-inch orifice because, you know, you go too small, it blocks and you get a blocked tank. So what am I left with if I use those two numbers? Well, all I can play with is the depth of water. So by doing my remodeling, to get 0.25 or approximately 0.25 CFS on 0.55 acre feet of volume, I can only put it under half a foot of head, which leaves me with a 215 foot by 215 foot footprint, or just over 1 acre of footprint with a low head to limit the outflow on a 4-inch orifice. You think that sounds ridiculous, but when I look at reality, we often see storage systems that encompass an entire site, almost an entire parking lot, that do go into these large volumes, and some of that is limited pipe depth or site depth, but other considerations are that it's very hard to limit the outflow with an orifice control if you try and put things deeper down, and as the poll said, the volume requires too much footprint. So can we use the vortex valve to solve this problem? And certainly you can. So one of the things to look at also is drain time. With the previous design, the drain time is very long as well. We're looking at 80 plus hours. So your cycle time on the tank is a consideration as well. So if I look at my hydro brake option and I look at, just say, let's use a 75 by 75 foot tank, run a 4-inch hydro brake so that I'm at the minimum discharge, minimum size on my outlet, and model that in HydroCAD, I find that I fill the tank to about 4.22 feet. My drain time's about 70 hours. That's a much smaller footprint. Problem is I'm under discharging now. I'm looking at a discharge of around 0.19 CFS. So I'm leaving some money on the table here. I need to improve this design a little bit. So I can go back into my system and remodel. And this modeling is not difficult once you've done one or two. It's quite easy to do and you do them fairly quickly. But I'm just demonstrating here what we're going to end up with. With some reiteration, I get down to about a 60 by 60 foot tank with a 4.4-inch outlet on the hydro brake. I fill that tank to about 5.47 feet with a cycle time of 52 hours, and my discharge is 0.24 CFS. So the hydro brake really does allow you to shrink that footprint. Providing you've got that available on site to drive that depth, you can do quite a bit in terms of reconfiguring your volume to a smaller footprint. And just by comparing the two, 4-inch minimum orifice, 0.25 CFS, storage depth is around about half a foot, 0.52 feet, but your footprint, 215 by 215 feet with an 80-hour drain down time. Using the hydro brake, I can actually increase my outlet size to 4.4 inches. I can drive that down to 5.47 feet, 60 by 60 footprint, and a 52-hour drain time. None of this has exceeded my allowable discharge. So downstream, things are actually in better condition because I'm not extending peak flow, so I'm actually mimicking the pre-development condition better. In fact, if I look at a 4-inch hydro brake and that 0.25 discharge limit, I could actually drive that down to 9 feet or 2.74 meters and still meet 0.25 CFS of discharge. So compared to an orifice control at roughly 0.52 feet. Sorry, I got a typo there. So it's the ability of the hydro brake to reconfigure a footprint is one of its main uses. So let's take a look at another case. Let's say you're going to do either a regional pond, much larger inflow area this time, much larger flow volumes, or it's an existing pond that may be under stress because of either encroachment of weed that is effectively shrinking the volume, or maybe some upstream development of that pond has changed the conditions, and that pond for some reason is stressed because it's a little bit undersized and you need to try and improve the condition. Well, one of the things you could do if you're doing, say, a regional pond is to go out and make the pond bigger. Well, that's expensive. So can we squeeze more water into that? And depending on the hydrograph, yeah, you can. So let's think of this. I'm going to use a Florida DOT hydrograph this time, just as an example. Let's say the pre-development site is 50 acres and this pond has been designed to bring the flow back to its pre-development condition. So the pre-development flow rate on this is 6.57 CFS. We're looking at a 7-inch rainfall event, time of concentration about 30 minutes. So again, going back into HydroCAD, we can estimate by modeling this roughly what the pond size should be, somewhere around 18 to 18.5 acre feet or 22,000, 23,000 cubic meters to get that pre-development flow under control. And again, I can go back and redo my modeling and look at an orifice control and look at the, assuming that we've got, say, 5 or 6 feet of depth available, it's a fairly shallow site, redo my calculations based on that and come up with a footprint area and I size my pond and I end up with this pond that's roughly 17.15 acre feet, 5.69 feet deep, and it has an outlet control roughly of a 10.4 inch orifice. So you think, oh, that's pretty good. Everything's looking good. But can we do better? Well, I can remodel that with a hydro brake, and I end up with the same set of conditions, but in this case, I'm going to a 19, almost 20 inch hydro brake on the outlet. And I'll get roughly a 6% saving in volume. Now I can translate that volume back into an area on the same sort of depth, and I find that I've roughly got about 1 acre feet of savings, which is 1,270 cubic meters. Now, if I'm retrofitting to an existing pond, that could be useful. If I'm building a new pond, that's pretty useful as well, because you can put a fairly good value on that. So let's say that hydro brake might cost somewhere in the range of $15,000 to $20,000. I think when you work out just the trucking of the material off-site for that, you'll probably get that payback. And if you're trucking material back in, then you're going to get a payback. And if you consider the long-term cost of a pond, and at some point you're going to need to clean it, then someone down the road is going to be really thankful you made that pond smaller than it could have been with a different outlet, because they've got to pay for that maintenance. So the hydro brake has both an immediate and a long-term advantage. Okay, so hydro brake flood valves. This is a step up to the big brother of the hydro brake. This is for regional catchment control, flood control. The hydro brake flood design was something we would do in-house, and these valves have been built up to roughly 10 feet or 3 meter outlet sizes, used for regional flood control, primarily in the UK at present. And also, these flood control valves are designed with adjustable inlets, so we can vary the flow through them by up to 20%. And the reason you'd want to do that is because when you're doing regional modeling on river catchments or river models, there's a degree of uncertainty. So the adjustability in the valve can help account for or compensate for regional uncertainty, and also for either climatic or development changes that might happen upstream. The main thing about these valves is they have to be there's a lot of design that goes into them structurally as well as hydraulically. They've got to be conceived correctly, designed correctly, fabricated correctly, and then installed correctly. We're still looking for a US, someone in the US to stick their hand up and say, yeah, I need one of those. But in the UK, we have multiple projects using valves like this, and they're all working successfully and doing very well. The main advantage of the vortex valve for these flood control type dams is that they work without anyone doesn't require any electricity, doesn't require any moving parts. There's no need to have a manual actuation. They just sit there and work. They're very robust. So now I'm going to just go into the design tool, and you should have all received a link to that when you got the invite to this presentation. I hope you've all gone on and registered for it and had a play with it. A couple of things to keep in mind when designing hydro brakes. Primarily, they're designed around a maximum discharge at maximum head. So you have that design point. And the head is the difference in water level. So if you're assuming free discharge, then we just usually assume that it's the invert outlet to the water level on the upstream side at peak discharge and at peak head. And if there's backwater conditions, then it's the differential head between the two water levels, upstream and downstream. Now, some of you might ask, okay, so if there's a backwater condition, where does the air come from? Generally, these valves, the negative pressures will draw air into them anyway, and they'll operate with an air core even though they're fully submerged. But in some cases, we will add in to what you see here is a slide gate on the back with a header pipe, and that pipe will introduce air. That pipe also has a couple of other uses. You could actually stand a vertical standpipe there and use it as a spill pipe. So at a certain water level, water could actually overflow, go into the valve, and it would actually depress the air core, and the valve would then flow at the full rate of the orifice on the outlet side of the valve, which would be an immediate jump up in flow. So you could install one of these valves and have a header pipe on it or a siphon pipe on it that would allow, at a predetermined level, a sudden and rapid increase in the flow. So if you had critical upstream levels that you didn't want to exceed, then that may be a way of handling that, or using a wear-over system. Now, the other thing you see here is there's a gate on the back of this valve. Most of our valves come with these gates, which are usually hooked up to a pull cord. They're a solid gate, and you could then open those gates manually if you required to increase the flow, or for inspection, or to allow cameras or jet systems to pass through them. So the valves can be maintained, cleared, and inspected very easily. Mounting, when you mount these valves, as I said before, every valve is a custom build. We tend to build them for a structure. The most common is a flat mount. In Chicago, this is a fairly common detail where they'll cast in or grout in a flat spot for the valve, although the valves can be made with a curved mounting plate that would go hard up against a manhole structure. And also, it's possible, when we do designs, often you have 5, 10, maybe a 50-year release rate, and you would stack orifice controls and model that. You can do the same thing with the valve. It's just a head discharge curve. You can stack the head discharge curves in your modeling software, and you can model valves in stacked conditions. Okay. Now, the online software, it's a really nice tool. It's simple to use. It'll give you several outputs. You'll get a drawing. You'll get a head discharge table drawing as well. And in addition, you'll get a CSV file which will allow you to import the head discharge data directly into your modeling software. So if you're doing modeling, and you can use any modeling software that allows you to put in a custom head discharge table. So if you can put that table in, you can use a valve. The only quirk I've noticed recently is that I've been using a free version of HydroCAD, and when I tried to import the CSV file, it didn't like the brackets with meters and liters per second there. And after contacting the HydroCAD people, they informed me to just delete the brackets and the units, make sure the numbers are actually in the units you want that the HydroCAD is set up for, and then re-import, and it worked perfectly. So if you have trouble importing, just contact your modeling software support, or just try looking at these headers. You might have to do some alteration editing to those headers. But other than that, imports very smoothly. So what I'm going to do now, I'm just going to flip out of this presentation, and I'm just going to bring up the modeling software that we have online. So it's hydrobreakoptimum.com, all one word. And you'll just log in. And there's not a lot to do here, but I'll explain, go through. You can select either English units or, this is a language thing, British language. What that really means is metric or imperial units. So the US site will give you feet and meters, and the British version will give you feet and meters, meters and liters per second. And that'll just change here. So you can just change it, and the units will change. That's the only thing that goes on there. You'll see the French version, that is not fully operational at the moment. So if you want to work in French language, that'll be coming soon. The first two, there's flyouts for help there, so no problem there. You just put in your head that you're working with, the flow rate that you're trying to design to. You've got to have a leading zero. You can't just put 0.25 or anything. It wants a 0 point in there. There are several options in terms of the valve. Minimize upstream storage is the default, and for 99% of the jobs, I would leave it at that. The next one down is minimize blockage risk. That maximizes the inlet to the valve. The valves are designed so that the inlet is always, the outlet is always larger than the inlet, but in this case, it will probably match the inlet and outlet and maximize the size of the inlet so that you minimize the blockage risk. The future proofing is the adjustable valve, and linear discharge is actually a not quite correct description. It's actually, it mimics an orifice. So you can use a valve to mimic the orifice discharge curve while still getting the benefits of the larger opening. Don't worry about the flush flow. That's an option that allows you to customize the curve a little bit. As you play with this, you can experiment with that and work out how to use it. Surface water, foul water, combined sewer options, depending on what you're using it for stormwater, mainly it's surface water. Whether you've got a sump available or not, if there's no sump available, it will force the selection of a C-type valve. If there is a sump available, it will probably default to an S-type valve. Mounting conditions, whether you want lugs, a flat mounting plate, a curved mounting plate for a manhole, or a spigot push-in type fit into a pipe. So there are different options there. For those of you that are perhaps listening in from the Chicago area who do designs to the City of Chicago standard, there is a specific drawing that the City of Chicago requires, and that will be added in as an option in the next few weeks, hopefully, that you'll be able to get the City of Chicago detail for submitting your drawings to the city. In the meantime, just email us your design and we will generate the City of Chicago drawing for you. And then you just hit design hydro brake. That's all there is to it. It usually designs within a few seconds. Just waiting here. I have a slow connection here where I am. And I'm going to get a error message here, but let me just reload that. It's something to do with Chrome at times. I'm not sure why it happens. I'm not going to spend too much time trying to get around that. It was working this morning, but every now and then Chrome, for some reason, throws up an internet blockage. It's going to... I apologize for this. Everything works until the time you go to it. Okay, it's reloaded it. Let's try another go. Okay. So it ends up with a quick design there. Shows you the head discharge curve that you're getting. As you scroll down, you'll find information about the valve, the design points, a bit of a drawing showing the minimum clearances. You'll get all that with the email it sends you. It tells you how big the valve is, so you get the outlet size. In this case, this valve will be 4.7 roughly inches in diameter on the outlet side. You then click these two options to get your result, and it's important to select what format. If you don't select any format down here, you're not going to get any answers. And so you'll get the drawings and the hydraulic data here, and you say generate email. Now that will go to the email address you use to register for. So probably within about 30 seconds, you'll get an email with those files in it, and it works fairly solidly. You can then bring that into your modeling software and you're good to go. So a very simple piece of design software. There is no save option here. You just have to come in and do your designs. The design tool just takes you back to a cleared screen, and the downloads will take you to our website where you can download product information. Just check that when you are on the correct website. Usually it picks up where you are and gives you the correct US or UK website. So that's the design software, nothing too hard about that. Feel free to use it as much as you like. You might get a message that after about 5 initial designs, you need to be approved for further designs. Just push whatever button you need to push to ask for approval, and you'll be approved to continue using it forever and a day. With that, I'd like to thank you for your time. It's been a pleasure presenting to you. If you have any questions, please just go through the follow-up exit survey. There's a place there where you can write questions, and we look forward to talking to you guys sometime in the future in a future presentation. Thank you very much.